Hi everybody, welcome back to Chem 140. I just checked my email and I got a ton of last call notifications for all my classes. Um, that includes us, so last call for quiz number 7 and lab worksheet number 4 is tonight. Tonight's a busy night for everyone in all of my classes, it looks like. Make sure you get those in by the deadline so that I can grade it. And yeah, we're going to work on stoichiometry tonight. So this is probably the most important exercise that we're going to do. In fact, I even write here, it's the whole point of 140. This is where we put everything together and do everything we've learned in this class pretty much at the same time in terms of calculations. So your goal is to be able to reproduce these calculations and then be able to do them again in 161 and 162. Excuse me. I realize that there's quite a bit of a delay between this and 162, which is when we're going to be using a lot of stoichiometry. And we do review it in 162, but it's really important to get the foundation down so that you are able to do these calculations. So yesterday we talked about figuring out the number of moles of a compound given the moles of a starting point. So like if I had 4 moles of A, I could figure out how many moles of B there were given a chemical reaction. Well, if I know what A and B are, and I know their molar masses, we can turn those into grams, or we can count particles using Avogadro's number. And so this calculation computation is called stoichiometry, and you've already done it before. This was the entire focus of Unit 13, so I've even given you a quiz on it. That quiz might be due tonight. Make sure you do it. So we're going to do more of that. So I'm going to give you this reaction here. This is the reaction for sodium azide. The way that this works, for sodium, I'm going on a tangent here. The way that sodium azide works in your airbag in your automobile is that you have a small amount of sodium azide inside a small chamber in the at the base of the steering column, and the steering column is connected to your airbag in your vehicle. The sample of sodium azide is connected to a circuit which is connected to your bumper. And when your bumper strikes or collides an object, it completes the circuit and ignites the sodium azide and produces nitrogen gas. The nitrogen gas then expands really quickly, filling that chamber, going up the steering column of your steering wheel, and filling the airbag, and the airbag deploys. So if you've ever seen an airbag go off, it's effectively instant, because you're producing liters upon liters upon liters of gas really, really quickly, because this reaction is fast. So let's study how much you need to fill an airbag in various conditions. So this first example is, I'm going to put 20 grams of sodium azide into the chamber, and I ignite it. How much nitrogen is formed in grams? So let's figure that out, because we know that for every 2 molecules of sodium azide you put in, you get 3 molecules of nitrogen out, according to the equation that's balanced. Now, instead of molecules, we could work with moles. For 2 moles of sodium azide, we would get 3 moles of nitrogen out. So we can use that to do calculations. And let's do that. Let me just zoom this in before I click over. Now, actually, before I do that, remember that we have this chart that's handy here. And we can identify what A and B are. So I'm giving you a mass of something. So we're going to call A is sodium azide. And that goes here. I want to figure out the mass of nitrogen. So B is going to be nitrogen, and N2 specifically. So we're going to start here and end here. I want to say that this is the class that I mistakenly wrote sodium azide. This is where sodium azide is. So you could see that NaN3, not the ionic compound you would have expected for sodium and nitrogen. That's because this contains the azide polyatomic ion, which is different from the nitride ion, which is N3-. And with a 3- charge, I should say. I know. Thanks, chemistry. Thanks for being confusing. But, you know. All right, so let's do our calculation here. I got to zoom this in a little more. So according to our little chart that you can't really see on the screen anymore, we are starting with grams of sodium azide, and we need to get to grams of nitrogen that is generated from this. Now I know that if I have some moles of sodium azide, I can figure out how many moles of nitrogen there are from the balanced chemical equation there, right? And here's our relationship. 2 moles of sodium azide is equal to 3 moles of nitrogen. Now, if we can just turn these from moles into grams, which we can do, we can solve the problem. So we can look up these masses on LenTech. So we'll go to our molar mass calculator. I basically have to just type the letter L and LenTech pops up on my browser. So according to LenTech, sodium azide is 65.01 grams per mole. So we'll write that down. 1 mole sodium azide is 65.01 grams. And then for nitrogen, I know that 1 mole of nitrogen is just twice what it says on the periodic table. So that's 28.02 grams N2. So now we have all these relationships, we can do the stoichiometry. So let's do that. So I give you 20 grams of NaN3. We're going to turn grams into moles. By doing that. And then we'll turn moles of NaN3 into moles of N2. So now we're there. And then we can finally turn moles into grams. I ran out of space because of course I did. And there we go. So once we hit enter on this calculation, we should end up with the number of grams of nitrogen. So let's do the numbers. So in 1 mole of sodium azide, there are 65.01 grams, like we said. For every 2 moles of sodium azide I put in, I get 3 moles of nitrogen out. And for every 1 mole of nitrogen, that's 20. This looks like a E. That should be a 2. 28.02 grams of nitrogen. Where'd my calculator go? There it is. So we'll punch it all in. 20 times 3 times 28.02 divided by parentheses 65.01 times 2. And I get 12.9 grams of nitrogen when I consider sig figs. Now, I'm actually typing this in the calculator. I just hit the wrong button here. So this is roughly half a mole. And for reference, at room temperature and regular atmospheric pressure, 1 mole of gas is about 22 liters. Now, I don't know how big the standard airbag is, nor do I know how big the steering column is that leads up to it. The steering column is probably very narrow to reduce the amount of volume wasted, and the box that this stuff is held in is probably very small too. So 12.9 grams of nitrogen would be about 10 liters of nitrogen produced. I want to say that an airbag is roughly 10 liters when totally inflated. So this is more or less about the amount of sodium azide that is in your automobile airbag setup. That's my estimate anyway. I'm not actually sure how big an airbag is, but this is a good estimate. It's a good starting point. All right, so I'm going to give you a micro experiment. We're going to work with a really tiny amount of sodium azide here. So now we need the equation again. So do I put that on the screen? I do. Okay. So now instead of you solving for how much nitrogen mass is generated, I'm asking you to solve for something different, but otherwise the problem is the same. So I'm asking you for the number of molecules of N2 to solve here, given this tiny, tiny, tiny amount of sodium azide that's used. How many molecules are made? So I'm going to have you start here and end here. And this is the same situation. A is still sodium azide, and B is still nitrogen. So I want you to try this calculation. Starting with that mass, tell me how many molecules of nitrogen are generated. Follow the exact same strategy that we did on the previous slide. I'll give you about 5 minutes to try it, and then we'll go over the answers together. See you in a bit. 2 more minutes and we'll go over the answers. All right, let's go over the answers here. Oh, I don't have everything on the screen here, so okay. There we go. So I'm giving you a small sample of nitrogen, sodium azide. So we're starting with a mass. And I want to find out how many molecules of nitrogen gas are generated from this. Now, I know that I can figure out the number of moles of sodium azide and turn that into the number of moles of nitrogen using the balanced chemical equation there. Excuse me. Ooh, frog in my throat. And just like before, for every 2 moles of sodium azide, we get 3 moles of nitrogen out. So all we have to do is get stuff to turn into moles and turn it out of moles. So we'll turn grams into moles. This is still the same as before. 1 mole sodium azide is, I've already forgotten, it was like 65.01, right? Yeah, 65.01. And then to go from moles of nitrogen to molecules of nitrogen, we just do the same thing that we would do for any time we're doing numbers. In 1 mole of anything, there are Avogadro's number of molecules of that thing. Now we have everything figured out. We can just set up the problem. So we'll do the dimensional analysis. Turn grams into moles. Then we'll turn moles into moles of nitrogen. and space is a thing, then we'll turn moles of nitrogen into molecules of nitrogen. And let's fill in the numbers. So 1 mole of NaN3 is 65.01 grams, which is what we decided over there. Not decided, we looked it up. For every 2 NaN3 I put in, I get 3 N2s out. And then in a mole of anything, there are Avogadro's number of molecules in the sample. So we put it in the calculator, and what do we get? 1.82 times 10 to the minus 6 times 3 times Avogadro divided by parentheses 65.01 times 2. And I get 2.53 times 10 to the 16 molecules of N2. So even though I'm using a microsample, I still have tons of molecules because, again, molecules are really tiny. All right, this one requires you to balance an equation and do this question. So I'm going to put 5 grams of nitrogen in the reaction vessel. I'm going to put abundant H2, so I have effectively infinite, and I want to make ammonia. How much ammonia do I make in grams? First, write out the balanced chemical equation. So you know what the reactants are. They're N2 and H2. You know what the products are, NH3. Balance the equation, and then tell me the mass of ammonia that I make when 5 grams of nitrogen is input with abundant hydrogen. I'll give you some time to work on this too. See you in a bit. 2 more minutes and we'll go over the answer. All right, let's solve this problem. So, first of all, we need to have the balanced chemical equation. So I'm going to write that on this page here. So in order to balance this, we need to balance N and H. You should be able to do that and get this as your result. And then we're doing the same process that we did before. Grams of N2. And I want to figure out grams of NH3. So there's our relationship. I'm not going to write the relationships on the side here just to save myself some space here. But this is the exact same problem that we just did at the start of today's lecture. So we'll turn grams into moles. Moles of N2 into moles of ammonia. And then we'll turn moles of ammonia into grams of ammonia. And so now we'll run the numbers. So let's look up the molar mass of N2. That's 28.01 grams per mole. That's off the periodic table. My relationship between N2 and NH3 is for every 1 N2 I put in, I get 2 ammonia out. And that's just these numbers right there. And then finally, for every mole of ammonia I have some number of grams. We can look that up on Lentech. It's about 17 or so, but we'll just type it in. NH3, 17.03. Oops, I didn't cross this out. That's okay. And then we punch it on the calculator. 5 times 2 times 17 divided by 28.01. And I get 6.07 grams of ammonia. All right, I have one more problem for you to practice with. And that's this one. Using the balanced equation that you had from before, I'm going to react 2.75 grams of hydrogen. How much nitrogen do you need? This is exactly the same type of problem we just did, so I'm just going to post the answer for you. You can do that practice on your own. And we'll go to this problem, which is just a different one. Oops, I didn't mean to do that. Okay. So here we have pyrite. Pyrite is also known as fool's gold. If you burn pyrite in the presence of oxygen, you get rust, which is iron oxide, and SO2. First, balance the equation. Second, how many grams of SO2 do you make when you combust 38.8 grams of pyrite? And from 38.8 grams of pyrite, how many molecules of rust are made? So go ahead and try these problems. Again, I'll give you about 6 or 7 minutes to do them. We'll go over the answers together. And then we're probably due for our break. So see you in a bit. 2 more minutes. We'll go over the answers then. All right, let's go over the solution. So first we got to balance the equation. So let me do that real quick. So if I put a 2 here, this becomes 4. And how much oxygen do I have? So I have 3. Heat is 11. So I actually need to do this. All right, that should be balanced. So 8 times 2 is 16. 22, 22. Heat, sulfur, 4 iron. There we go. So a little bit complicated for balancing that equation. But that's what I got, 4, 11, 2, and 8. How many grams of SO2 are produced when 38.8 grams of FeS2 are combusted? So we'll go over here. So I have grams of FeS2, and I want grams of SO2. I know that if I have moles of FeS2, I can then convert to moles of SO2. And turning from grams to moles is trivial. If we have Lentech, we could just look up the molar mass. So let's do that. So first we'll convert grams of FeS2 into moles of FeS2. And then we'll turn moles of FeS2 to moles of SO2. And then finally, we'll turn moles of SO2 into grams of SO2. And we'll go look up those relationships on Lentech. So the molar mass of FeS2 is 119.98 grams per mole. The ratio between FeS2 and SO2 is 4 to 8, using the balanced equation up there at the top. And then the number of grams of SO2 per mole is 64.06. So I'm going to type this in. 119.98 times 4. Got 41.4 grams of SO2 are generated. So that's the first one. And then the second one is how many molecules of pyrite are generated. I'll just scroll down a little bit for that. We're doing the same thing here. So we got grams of FeS2. Except instead we're going to go into moles of rust. Oops, you can't see that, but I'll scroll back up. And then we'll turn that into formula units or particles of Fe2O3. So there's our blueprint right there. You can barely see it because I'm going to scroll this up in a second. There we go. So now we can do our dimensional analysis here. Grams turns into moles. Moles of FeS2 turns into moles of Fe2O3. And then moles of Fe2O3 turns into formula units or F units Fe2O3. And this should be the same molar mass as before, which is just right here. We'll scroll up, 119.98. The relationship between iron FeS2 and then Fe2O3 is 4:2. That's the balanced equation on that slide. And then in a mole of anything, there are Avogadro's number of units. All right, so we got 38.8 times 2 times Avogadro's number. That's the wrong button. There we go. Divided by parentheses 119.98 times 4. And I get 9.74 times 10 to the 22. That should be a 9. There you go. So that's how you do those problems. You know, for the all 0 people that are watching. Oh, now I have 1 person watching. I had 0 for a long time. So after the break, what I'm going to do, so we're going to take a break now. But after the break, what I'm going to do is, unless somebody says something, I'm just going to go through all the problems. So not like wait 5 minutes, let you try it. Just because I have a lot of problems left to do, and I want to get them done today. So we'll take a 10-minute break, and then we'll just start doing lots of problems. You can pause the video if you want to see the work on them on your own and do the solutions. And when we get back, we'll continue our conversation with limiting reactants. So see you in a little bit. Alright, we're back. So I'm just going to be doing these problems for practice. You can pause the video at any point if you'd like. Since it looks like I don't have any viewers still. Maybe one. It's bouncing between 0 and 1. But yeah. So, we're going to talk about the limiting reactant. The limiting reactant is just an application of stoichiometry. And what it is if we... all the problems we've been doing so far have made an assumption. And that assumption is, oh, I have a limited amount of one thing that I said in the problem, but the other thing I have abundant. So like in the problem with nitrogen and hydrogen to make ammonia, I said I put in 5 grams of nitrogen and all the hydrogen that I need. So as much, infinite hydrogen, whatever. But realistically, that's not possible, right? You can't put infinite of something in a container and then limit with the other thing. Now, you could put tons of it, but usually that's pretty wasteful. So what's a more appropriate action to do is that we put a small amount of both things in there and we do the calculation twice and we see which one produces less, because that would be the one that limits our reaction. The one that makes less stuff must run out first. Otherwise, it'd keep making products, right? So that's where the premise of the limiting reactant comes in. We're going to simulate that by using this really simple formula to make a cheeseburger. So I put 2 patties, I put a bun, I put a cheese, I get a cheeseburger. Now, let's suppose that you had these ingredients. I have 10 patties, 6 buns, and 8 slices of cheese. How many burgers can you make? Well, if I do this, I'm going to run out of hamburger patties first, because with 10 patties, and each burger needs 2 patties, I can make at most 5 burgers, right? I could do the dimensional analysis with anything else, and I'd be able to make as many as I have, because, for example, for 6 buns, you need 1 bun per burger, so you could make potentially 6 burgers if you had abundant everything else. And with the cheese, you could see that we would get 8 burgers. Now, each time you do this calculation, it is, again, assuming that you have abundance of all of the other things. But in reality, you don't. So you could see here that the patties limited the number of burgers that I can make. So these are the limiting reactant. The other things made more than the limiting reactant, which means that we had these substances in excess. We had this in excess too. Since I can't just make a burger out of a bun and cheese, those extra things just hang out. They're unused. We ran out of burgers, no reason to serve out the buns and the cheese. We'll wait until we get more hamburger patties. So when you do calculations with 2 reactant quantities, you do the calculation twice and see which one produces less. Otherwise, it's exactly the same as what we've done. We're just doing the problem twice. Now, when you do the problem twice, you're going to identify one thing as the limiting reactant. So you'll need to make sure that you indicate that, because on the quiz, you may need to know that information. I might ask you for it. So let's suppose that I do this reaction. 2 hydrogen and 1 oxygen makes 2 water. I can write that like this, which I can then convert into grams. So if I put in 4 grams of hydrogen and 32 grams of oxygen, I will make 36 grams of water. But if I put in extra stuff, for example, I put in 40 grams of oxygen instead of the 32 that was needed, then what would happen is I would use up all this hydrogen, and I would still make 36 grams of water. But the remaining oxygen would just hang out. It's left over. And once I'm out of hydrogen, I can no longer continue the reaction. The reaction is done. there's nothing else to make. So in this case, hydrogen is the limiting reactant. Now, by just looking at masses, you can't really tell this. So what we need to do is we need to take our masses, turn them into moles, and then turn them into moles of our product, and then turn it into grams of the product to see what is happening here. Whichever one makes less is the limiting reactant. Now, you can do this in a shortcut method. You could choose a product and just figure out the moles of that product instead of going all the way to grams. I'm going to just convert everything directly to grams, but you can stop at moles because the relationship between moles and grams is fixed, right? If you make fewer moles of product, that's still the limiting reactant. But students seem to find it to be a little easier if you just turn everything into grams and then compare them at the end like that. So that's what I'm going to be doing. So for this first example, we're going to take 40 grams of methanol and burn it with 46 grams of oxygen. How much CO2 is made, and which substance will run out, which is the limiting reactant. So let's do that. I've already balanced the equation for you. But for each of these types of problems, we're going to do the same thing. So we're going to do grams of the starting reagent or reactant. We'll turn it into moles of the starting reactant. We'll turn that into moles of CO2. And we'll turn that into grams of CO2. So we're going to do the same problem twice, more or less. So this is methanol. And 46 grams of oxygen. Now be careful. Don't just look at the thing that there's less of and say, oh, that's going to run out first. Because bigger molecules weigh more. So I might give you like a large mass of a large molecule and a small mass of a small molecule, and it just turns out there's fewer molecules by number in the bigger mass. Not always, but sometimes. So to solve this problem, we would do the same problem we did in the previous section. We'll turn grams of methanol into moles of methanol. I'll turn moles of methanol into moles of the thing that we're trying to solve for, which is CO2. And we'll turn moles of CO2 into grams of CO2. And then we'll go run the numbers. How many grams are there in a mole? Use Lentech or the periodic table. So 1 mole of methanol is 32.04 grams. According to the balanced chemical equation, I put in 2 methanol and I get out 2 CO2. And in 1 mole of CO2, we have... Oops, that didn't work. Hold on. CO2. 44.01 grams of CO2. So if I reacted 40 grams of methanol with abundant oxygen, I could make up to 40 times 2 times 44.01 divided by 32.04 times 2. Looks like 54.9 grams of CO2. So if I run out of methanol first, I make up to 54.9 grams of CO2. Let's do the same calculation with oxygen and see how much 46 grams of oxygen would make. So grams of oxygen, moles of oxygen. Moles of oxygen to moles CO2. And then moles of CO2 to grams of CO2. And I didn't cancel out my units, but that's okay. We'll just do that now. We'll fill this in, 32 grams per mole of oxygen. According to the balanced chemical equation, every 3 oxygen I put in, I get 2 CO2 out. And a mole of CO2 is still 44.01 grams. And how much CO2 is potentially made with 46 grams of oxygen? 46 times 2 times 44.01 divided by parentheses 32 times 3. You'll notice that I got less CO2. So potentially 46 grams of oxygen could produce 42.2 grams of CO2. Because that is the smaller amount, oxygen was the limiting reactant. So this is the answer we would submit. If I mix 40 grams of methanol and 46 grams of oxygen, I get 42.2 grams of CO2. Heck, if I added 1,000,000 grams of methanol and 46 grams of oxygen, I'd still only get 42 grams of CO2. Since this one has more, it's an excess, which I'm going to label as this, excess. What do we do with the excess number? We do this to it. Woo! We cross it out. It's not helpful to us. You do not enter this as your answer. You don't add them together. You don't do anything with it. You just cross it out. Now, I didn't obliterate it because what if we needed it for a different problem or something like that? That information could still be useful, so we'll leave it there. In this particular case, it's not. But there are other practice problems in the text and the worksheets that might ask you like, oh, well, how much of the other leftover thing do you have? And you could go back and subtract. So my slides do that. They only convert to moles of CO2, but you get the same result regardless. So you could have stopped at this point in the calculation right here. Oops, where'd my pen go? So you could have stopped right here in both of these and gotten a number of moles of CO2 and then just chosen the one that's smaller. But I feel like for an introductory class, we'll just do the problem all the way through. It's good practice. And then you just circle the smaller number at the end. All right, let's do another one. I have these two things. This equation is already balanced. All ones. I know that that's strange, but sometimes it does happen. I'm going to do 100 grams of PF3 with 50 grams of F2. And this isn't scrolling. Oops. Can I make this bigger? Yeah, there we go. All right, so same process since we're going from mass to mass. We're going to do grams of starting reactant. We'll turn that into moles of starting reactant, which will then turn into moles of the target product, which is PF5. And then we'll turn it into grams of PF5. Oops, you can't see half of that. Sorry. There you go. So same thing, 100 grams, PF3, 50 grams, F2. So we'll turn grams into moles, moles of my starting amount into moles of the target amount, PF5. Moles of PF5 turns into grams of PF5. And then we do the numbers. Where's Lentech? There we go. PF3. That didn't do anything. PF3. 87.97. Balanced equation is 1 to 1, so we just put 1s there. And then PF5, 125.97. I'm on the wrong screen. There we go. All right, what do we get? I get 143.2 grams of PF5. So potentially from 100 grams of PF3, I can make up to 143.2 grams of PF5. Well, let's look at fluorine here. So fluorine, we're going to turn grams into moles. We'll turn moles of fluorine into moles of PF5. Well, we'll turn moles into grams. We got fluorine here. Fluorine is 38 grams per mole, I believe. I should probably check that. Yeah. Still 1:1. And then this is the same as before. We punch it in the calculator. And I get 165.8. Okay, which one makes less? This one does, so because it is the limiting reactant. This one is an excess. We scribble it all out. We don't use it in our answer. There you go. All right. For our last problem here, we have thermite. And what I'm going to do is I'm going to post these links in the chat, which I don't know if you'll be able to click on. But give me a second here. So we're not going to watch these because there's nobody to watch them. So you can watch them on your own time. So let me see. Hyperlink. Oh, I don't want to edit the hyperlink. I want to... Oh, I see what happened. Okay. Edit hyperlink. Copy. So one of these is thermite done in a classroom, which is this one. And then I believe the second one should be a video from Mythbusters. So there's those links that you can watch if you'd like. The first one got cut off. You can ask me for the link if you really want, or just look up thermite on YouTube. You'll probably find these. But the thermite reaction is a very popular chemistry demo that's done because you generate molten iron. And it says on the screen it's really cool, but in reality it's really, really, really freaking hot because you're making molten iron. And so in the Mythbusters video, they make molten iron in a large enough quantity that it cuts a car in half. So they pour this thermite, they ignite the mixture, and it basically looks like lava is running down the front of the car, and it tries to they try to cut the car in half. And I think they're more or less successful. But you can watch the video on your own time if you'd like. So we're going to do this problem. We're going to put 5,000 grams of aluminum and 30,000 grams of rust. How much molten iron is made? So there's our 5,000 grams of aluminum. And here's our 30,000 grams of rust. It's a lot of rust. All right, and our strategy here is to go from our massive starting reactant again, turn that into moles, and you'll notice that the process that we're doing these types of problems, it's the same every time, right? But I do want you to have enough practice for stoichiometry so that when you get to the quiz, you're like, oh, this is easy. We did 60 million of these. So we'll turn moles of aluminum into moles of iron. moles of iron into grams of iron. All right, so according to the periodic table, the aluminum molar mass is 26.98. For every 2 aluminum in, I get 2 iron out, and 1 mole of iron is 55.85. I didn't cancel these. There we go. So how much iron do I get out? It's probably a lot, because 5 times 10 to the 3 is a lot. To be working with. And I get 1.0 times 10 to the 4 grams of aluminum. I get 10 kilograms of molten aluminum by doing that. Okay, cool. Let's now do the same thing with our rust down here. So we'll turn grams into moles. We'll turn moles of iron 3 oxide into moles of iron. And we'll turn moles of iron into, oops, I gotta cancel, grams of iron. 1 mole of iron, let's go to Lentech. Where did it go? There it is, Fe2O3. That's not what I meant to type in. I typed in F32, Fe2O3. 159.69. The relationship between moles of rust and moles of iron is 1 to 2, according to the balanced chemical equation. And we have that many grams of iron, so we'll type it all in the calculator. So 30,000 times 1 times 2 times 55.85 over 159.69. And in this case, I got 21,000 grams of iron. So what's the limiting reactant? In this case, it was the one that I had less of, believe it or not. So this is LR. This is excess. We scribble out the excess. Don't need it. All right. Do go watch the thermite reaction, though. It's really cool. All right. I'm going to skip this problem. I'm just going to leave this for you to try. There is a challenge problem at the bottom if you'd like. But we've done like 4 of these. I don't need to do a 5th one. If you have questions about it, you can poke me in the Discord. Send me an email, and I'll give you the answer. I just want to get through reaction yields so we're done with Unit 15. And so next week, we only have Unit 16. Oh, someone's meowing. Who is it? Yeah, I hear you. Meow. I shouldn't encourage her. Oh, it's too late. Here's Maya. So when we do a reaction, we've sort of been working on the assumption that our reactions will go to 100% completion and that all of a reactant will be consumed. Now, it turns out there's reasons for this not to happen. So the first that we're going to talk about in 163 is equilibrium. Equilibrium is a competing reaction. Generally speaking, this is where products get reverted back to reactants. Maybe because the reactants are more stable than the products, and you only make a small amount of products. You could also have other reactions that you don't intend to due to odd conditions that you may subject your sample to. For instance, in the lab that you watched the hydrate get dehydrated for, if you heat it too hot, you could actually decompose the sample, and then you lose something other than water, and you get a weird result, and the reaction is not 100% complete. Sometimes products decompose, and you just get other random junk that you don't want. And then there's also the possibility that you might just drop everything on the floor. So these are all things that happen. Your yield is what you physically get into like the bin at the end and say, this is what I made. And not all of it's going to get there. Maybe when you were scraping it into the bin, some of it was left on the tool you used or the container it was held in. You're not going to be perfectly able to get everything out. So what you actually produce and give to me, the person evaluating your reaction, I guess, is called your actual yield. This is what you actually did. Now, all of the calculations that we've done to this point are theoretical, because we're not actually doing these things in the lab. We're just talking about the lab, right? So those calculations are called theoretical yield. Anything you do with a calculation is theoretical. Anything that you produce by actually doing the chemistry in an experimental situation is the actual yield. And we could just take the ratio of those two things together to get percent yield. What you got divided by what you should have gotten according to the calculation you did on paper is your percent yield. Now, there's all sorts of different problems that we can do with this. The simplest one is going to be, okay, here's the reaction you did, and here's the result that you got. What should you have got? So calculate the theoretical yield, and then find the percent yield. So that's what we're going to do for the rest of the periods. We're going to talk about percent yield. So let's do an example here. A student reacts 4.7 grams of hydrogen with excess nitrogen. So this is not a limiting reactant problem. This is like the old stoichiometry we did at the start of the period. And I got 12.5 grams of ammonia. What is the percent yield for the student's reaction? There's our balanced equation there. So let's figure out theoretically what they should have gotten if the reaction went to 100% completion. Oops. There we go. So in theory, so we'll call this theoretical. We put in 4.7 grams of hydrogen with excess nitrogen. So hydrogen is the limiting reactant. And we're going to do our stoichiometry like we've done all along. Grams to moles to moles. We want NH3 to grams. So we have this like gamolmaga thing. That's what we're doing over and over is gamolmaga. So we'll turn grams into moles. We'll turn those moles of hydrogen into moles of our target, which is ammonia. And then we'll turn those moles into grams. And then we just run the numbers. So 1 mole of hydrogen off the periodic table, that is 2.01. I can't read the number. 6. There we go. For every 3 hydrogen I put in, I get 2 ammonia out. And then 1 mole of ammonia is 17.0 something. I gotta look that one up. oops, where did it go? There we go. NH3. 17.03. So I'll punch all that into the calculator. And I got this, 26.5 grams of ammonia should have been made, in theory. Now the actual yield that the student got was 12.5 grams. So they did the reaction. They put all the substances into the pressure cooker or whatever, and out distilled 12.5 grams of ammonia. What's the percent yield for the reaction? So the formula for percent yield, oops, we need the theoretical yield on the screen here. So percent yield is actual over theoretical times 100%. And that would be 12.5 over 26.5 times 100%. The grams cancel out. And what do we get? 47.2%. Now, if your first response is, man, that student sucks, they only didn't even get half. Turns out that this reaction is very, very difficult, and 47% might actually be well beyond any industrial process. It is common in organic chemistry to have reactions that have 20 to 30% yield. So don't look at a percentage and treat it like a grade, because it's not. Otherwise, we're all failing. We're all just trying to scrape by, you guys. Don't be so hard on everybody. So sometimes percent yields can be very low. Now, it is also possible to do a calculation and get a percent yield that's over 100%. And if you do that, that is a surefire way to indicate, oh, I messed up. My sample isn't pure. Because the theoretical yield tells you the maximum you should get. And if you get more than that, 99% of the time, what that means is your sample is wet. There's water in it. So use percent error as a tool and not an arbiter for judgment, is what I should say. All right, that's percent yield. That's how we use it. Any questions, let me know. Apparently got 47.0. That's fine. All right. Let's do another one. We're going to synthesize copper from this reaction. Now, I haven't balanced it. We're going to have to balance it first. Now, the chemist used 96 grams of aluminum. When her experiment was done, she obtained 87.7% yield. How much copper was recovered? So now you can see, oh, I'm starting to make these like a puzzle, right? We're going to have to use the formula to figure out what the answer is. So first we got to balance the equation. So let's do that real quick. You pause the video. I'm just going to put the answers in. So spoilers, here's the answer. There you go. That's the balanced equation. Give myself a little more space here. And we'll do it again. Wait, what the heck happened? Why did I end up all the way down here? There we go. I zoom in on accident, maybe. All right, so we don't know the actual yield. We're trying to solve for that. But we can always calculate the theoretical yield if we're given one of the reactants. So I'm given 96 grams of aluminum, and we're going to assume that there's excess CuCl2. It doesn't say that, and it really should. So, same thing as before, we're going to do gamolmiga. That's now my favorite thing to say, apparently. So, we did aluminum, and our target is copper. So we're going to turn this into... There we go. It's catchy. It's gamolmiga. So we'll turn grams into moles. And then we'll turn moles of aluminum into moles of copper. And then we'll turn moles of copper into grams of copper. And I have a periodic table right here. I really need to, like, get a bigger one of these and just, like, pin it on my wall. 26.98. According to our balanced equation, for every 2 aluminum I put in, I get 3 copper out. And a mole of copper is 63.55. So in theory, I should get this much copper. $339 grams. Now, I don't know how much she actually got, but I do know that if I look at the percent yield, which is, I wrote the wrong letter, sorry, which is actual over theoretical times 100%, her percent yield was 87.7%. And I know the theoretical yield, don't I? So all I got to do is solve for the actual yield, because this equation only has one unknown in it, so I could solve for that. So I'm going to rearrange the expression. So her actual yield is equal to 87.7% divided by this on 100%. So I'm going to move this over. And I'm going to move the theoretical yield over too, which would be, these units cancel out. I get 0.877 times 339 grams of copper. So her actual yield is 0.877 times our answer, or 297. So there you go. There are all sorts of different questions that can be asked about that using this formula. Just like we manipulated the percent mass formula, we can manipulate the percent yield formula too. All right, I have another reaction here, and I have more practice problems to do. Is there anybody? Let me double check to see if there's anybody watching. Nope, totally nobody at all. Everyone has abandoned me. Nobody cares about chemistry. So I'll just do these. Let me erase this screen real quick. Boop. I do want to check, is this the last slide? Yeah, it is. Okay, cool. And I have 10 minutes, so I'm going to do the problem. I'm on the wrong screen, though, so there we go. So, oops, that's also the wrong screen, but it looks like the right screen. It's just trying to trick me. Okay, so we're going to balance the equation, so let me do that real quick. Not with that end of the pen, I'm not. There we go. 2, and that's not where a 2 goes. Sorry, ignore that. There we go. So there's my balanced equation. So if I put 25 grams of zinc into the silver nitrate solution, I get a 72.3% yield of silver. How much silver came out? Let's do that one first. Oh, that's perfectly fine. Good. We'll scroll up. So same thing as before. Let's figure out the theoretical yield that I make from 25 grams of zinc. So I'm going to turn that into, from grams to moles, we're going to do our Gamolmaga. Oops. We want to solve for silver, so we'll do that. So moles of zinc, moles of silver, moles of silver, 2 grams of silver. Okay. Let's find the periodic table. Where is it? There it is. So I need zinc, 65.38 grams per mole. According to my balanced equation, for every 1 zinc I put in, I get 2 silver out. That's a deal. I'd much rather have the silver. And then 1 mole of silver is 107.87 grams. So in theory, how much silver do I get? 82.5 grams. There's my theoretical yield. Now, my yield was 72.3, so my percent yield, which is actual over theoretical, times 100%. I know what the actual yield is. That's 72.3%. And I know what my theoretical yield is, just this. So we can solve again for actual. So 72.3% divided by 100% to cancel those units, times the theoretical yield of 82.5, and I get 59.6 grams of silver was what was actually produced by this scientist's experiment. And then a student, excuse me, a student does another experiment with 30 grams of zinc and recovers 72.6 grams of silver. What is their percent yield? I don't have enough space, so we got to erase this again. So let's figure out what they theoretically should have made. And the process is the same, even though I erased it. I'm not going to rewrite it there. Hopefully by now we've done so many of these, you're like, oh my god. I get it. I get how to do it. Don't make me do any more of them. And that's kind of the point, right? I want you to get to the point where you're like, oh, I hate this. This is such a waste of time. I know how to do it. That's good. You learned something, right? I've already forgotten these numbers, so I got to write them down again. Let's see here. 65.38. I think it was 1 zinc goes in and 2 silver comes out. I should probably check that. Yep. Okay. And my screen disappeared. Hold on. There it is. And this is 107.87. Yeah. 30 times 2 times 107.87 divided by 65.38. So, in theory, this student should have made 99.0 grams of silver. But their percent yield, which is actual over theoretical, they actually produce 72.6 grams of silver. So their percent yield was 73.3%. All right, there you go. That's Unit 15. So those are the most important calculations, I think, in all of this course. If you can make it here, you can make it anywhere. Probably because we need all of that stuff here, which is ironic because nobody is actually here to make it. But, you know, that's just me being That's just me complaining that there's nobody here. All right. You would get a celebratory artillery orc if you were here, but nobody's here, so nobody gets it. Instead, we'll just go to the title card. And we'll call it a day. Because I'm done. I'm exhausted from this week already. And even though we got Monday off, so... let's review what we've got going on. So next week is Unit 16. There is a lab number 5. It involves Unit 16, so as we talk about Unit 16, I will also talk about the lab. But yeah, we are on the home stretch, so hang in there and make sure you'll get all that work done. So last call again for quiz number 7 and lab worksheet number 4 is tonight. Get that in by the midnight deadline, and we'll see you next week. Have a good one.